very well, and the spin-up electrons don't move so well. So it depends on which material you look at, whether in a ferromagnet your spin current is mostly carried by spin-up or mostly by spin-down. And it's even more complicated than that. But then the next thing what you can see then is you can look at how this difference of density of states at the Fermi level, how big it is, because it determines then how big the spin polarization of your current is. And so you can take this difference of the density of states and divide it by the sum. And if you do this and you can measure this experimentally, you see that in most common magnetic materials like cobalt, iron, nickel, and so-called permalloy, the spin polarization is of the order of 40 to 50%. But there are a couple of materials like manganites, what Dario likes to work with, or chromium dioxide, where the spin polarization can be very high, close to 100%. And so you see here in chromium dioxide, it's not so easy to see, but at the Fermi level here, which is this line, you only have spins of one direction available. And so therefore the current is only carried by one spin direction. So then the next question is, okay, if in a ferromagnet the electric current is spin polarized, can I generate a spin polarized current in a non-magnetic material? And the answer is yes. So what you can do is you can take a ferromagnet, put it next to a non-magnetic material, and then by driving a current from here to there, you generate a spin polarization. You see, if I close the switch here, you generate a spin polarization, and you get a splitting of the chemical potentials in this non-magnetic material, where you have more of one spin direction versus the other. And if you remember what I said before, this can be either spin down or spin up. It depends on the magnetization, on the band structure of the material that you look at. And here, for simplicity, I used a half metallic material, but if you use a more regular transition metal experiment where the polarization is not 100%, similar arguments still hold. It's very similar. So now, once you know that you can inject spins from a ferromagnet into a normal metal, you can make various devices from that. And so the simplest device is a two-terminal device, where you have two ferromagnetic layers, and in between you put a non-magnetic material. And the resistance of these structures is then determined by what the magnetization state of the two end materials is. And this is the basis for so-called giant magnetoresistance and magnetic tunnel junctions. And so this was first discovered in 1986, simultaneously by one group in France around Albert Fert, and another group in Germany, in